Great to have him give a talk. So yeah, go ahead.
Thanks, Satya. So one thing is that actually I had like a throat inflammation, I guess this week. So you will see me like drinking water a lot. So I hope you don't mind. Yeah. So hello everyone. My name is Yaoqing Yang. Today I'm going to talk about our recent work on the robustness of machine learning models. In particular, we'll talk about a novel metric called boundary thickness and show how it is correlated with robustness. So this joint work with my advisors and collaborators in UC Berkeley. So it is now well known that the prediction of cutting-edge machine learning models, such as neural networks, can sometimes be less robust than human being. So if we add some tiny perturbation to an image, human can easily recognize the image. However, it turns out that for an artificial neural network, a small but adversarial perturbation can completely change the prediction of the network. For example, from a stop sign to a yield sign, which clearly raises a big safety issue. Pictorially, what is happening is that in the high dimensional space, everything is close to the decision boundary. The stop sign image is really close to the decision boundary that even if you change just a little bit, you can change the prediction result. So this clearly raises a big robustness issue in utilizing neural networks. Adversarial robustness is not the only robustness issue that we will talk about today. We're also concerned about the so-called out-of-distribution stuff in real-life scenarios. For example, here I'm showing some common image corruptions and perturbations that can happen in nature. When you train neural networks on clean images and test them on the corrupted images, there's often a non-negligible gap. So we will also talk about that. So there are many different ways that people have come up to explain the robustness issue of neural networks. In today's talk, we will mainly focus on the overfitting aspect. So what does overfitting in robustness look like? In 2016, Tenay and Griffin show that adversarial examples arise because the decision boundary is very close to the so-called data submanifold. So in this plot, you can see that the black curve is the submanifold of sample data, and the decision boundary, which is the red curve, lies very close to the data submanifold. This is not good for robustness because basically you can change each sample just by a little bit to let it cross the decision boundary and go to the other side. So the authors show that if you have limited data and you train a network to overfit to this limited data, this is basically what will happen. Another aspect which is sort of related is that the neural networks often focus on some trivial features that are correlated with the prediction, but very fragile and non-interpretable. Being fragile means that these features can change easily if there is some perturbations on the data. The authors of this paper, which is about the non-robust feature, shown here, call these features the non-robust features. I don't have much time to talk about the details of the paper on non-robust features, but I think an intuitive way to think about this is that, for example, horse images usually have a grassland. So the neural network can use this grassland to identify horse images. Then the grassland in this horse image can be viewed as a non-robust feature. And this is because the neural network is overfitting to the samples in this particular data set, which might have happened to put all the horse images with the grassland. But of course, the non-robust feature might not be something that is meaningful to human. So this horse and grassland image is just an example to help us understand non-robust features. But in general, it can be something that is very noise-like, and is just from the fact that the neural network is overfitting to this particular data set. Another paper which comes recently says that overfitting issues are very common in the so-called adversarial training. So adversarial training is the scheme when you explicitly include the adversarial examples into the training process. So that is shown to be one of the best adversarial defense schemes. But this paper, shown on the bottom of this page, shows that the adversarial training procedure can lead to overfitting. So if you look at this blue curve, you can see that after epoch 100, the test error actually goes up, which is to say that if you continue to train a neural network, you're likely to overfit. In this talk, we're going to propose a way to sort of measure and mitigate the overfitting issue in robustness problems. But before we go there, I want to clarify a little bit about overfitting in robustness. So let's say we have two types of decision boundaries that can partition triangles from the circles, one on the left and one on the right. Then which one do you think is better from the perspective of reducing overfitting? So we notice that if you think in the way of curve fitting, you will probably say that the one on the left is better because it is smooth and has low complexity, which according to the so-called Occam's razor principle seems to be better. However, when we look at the decision boundaries, the one on the right is actually more robust. It's more robust because it has a larger margin. So this is just a quick clarification of the overfitting issue in robustness problems.
So can I ask a question? So is this so this is not clear to me that the decision boundary on the right is better. It's the margin is so the margin is bigger, but it can be arbitrarily more complex, right? So in this case, it's not necessarily arbitrarily more complex, but if you just rely on margin, I can make up a really weird notion of margin that makes it very big, but it's not very robust to some perturbation of data. So are you gonna talk about more clearly what you mean by the notion of margin and how that relates to the kind of the complexity of the of the decision boundary?
Yeah, that's a very good question. So I guess I should have clarified what I mean by a margin here. So basically, what I'm looking at is the input space margin. So what you see here is the input space. You have these triangles and circles, which are in the input space. And this decision boundary is basically the place that you have the fx equals to 0. So if you have fx greater than 0, you will say this triangle. If it has fx is smaller than 0, it's a circle. And then the margin is defined as the minimum distance that you can project a sample to the decision boundary. So
so measure of distance. There are many ways to measure distance.
Oh, I see. So I guess, in this paper, I think we mainly talk about the L2 distance.
Sure, okay.
Yeah. So I guess, there are many different ways to define distance. Of course, I guess there are some recent papers show that this distance can be correlated with each other. But I guess what I'm trying to say here is that if you consider the input space, and if you consider the margin to be the minimum distance that you can change the sign of a sample, then that is directly related to the robustness that people understand. Because when people define robustness, basically what people mean was that you can add some perturbations to the sample, and then you want the sample to have the same sign, right? So that is, I think, mathematically equivalent to saying that it has an input space margin that is big, right? So yeah, from that perspective, I think, yeah, the margin can indeed measure robustness.
Sure, great. I have more questions, but I won't interrupt your talk anymore. So go ahead. Thank you.
I have a question. Although the margin look bigger in the right side, but that is based on the samples which are being looked at. So maybe if we have more better diverse sample, for example, if I have more red points which are there in a line parallel to the first one, then that margin might not be good, kind of thing. So this is assuming that the training sample capture the diversity and everything properly, and then we are trying to basically having the margin.
Yeah, so I guess what I'm showing here is basically just an illustration. So this is definitely not what is happening in the high dimensional space. In high dimensional space, for example, you can have, like maybe 1,000 dimensions, and when you project it to each dimension, you might have a different plot, right? So what I'm showing here is basically just a pictorial illustration of what is happening when you want to compare two different types of distant boundaries in a very toy setting. So in this case, it's like, let's say we only consider 3 samples. And if, let's say, we consider a 2-dimensional input space, in this case, the right one will have a larger margin. But of course, if we have a larger sample size, then of course we have to define a way to better measure this margin instead of just do some visualization, I guess.
Yeah. Okay.
Yep. Okay, I guess this is just a quick clarification of the overfitting issue in the robustness problems. When you look at distant boundaries. Okay, so today I'm going to propose a new concept of neural networks called boundary thickness. So this is a generalized concept of margin, and is strongly correlated with robustness and overfitting in reversely trained neural networks. Now I'm going to show you 2 different types of distant boundaries. In each figure, we plot 2 level sets, fx equals to alpha and fx equals to beta. So this alpha and beta are 2 hyperparameters. Then we will measure the distance between these 2 level sets, and we will call that the thickness of a distant boundary. So the intuition of this figure is that when the distant boundary is thin, it is squeezed easily inside the narrow space between different classes of training samples. The boundary looks simple, but the robustness is low. However, if we can generate a thick distant boundary, then the neural network needs to make the distant boundary more complex. So fitting data becomes harder. However, in this case, robustness is actually better. Okay. So just to quickly show you, we have a formal definition of boundary thickness, but it's really just a mathematical description of what we are showing on this plot. So basically, we're just trying to measure the distance between the 2 level sets of a distant boundary. So you don't really need to pay too much attention to the mathematical definition. So basically, we're just measuring this distance here.
So is that correlated with the magnitude of the gradient?
Yeah. We haven't done any experiments to actually verify that, but I think it is definitely related. Maybe it's related to like the Lipschitz constant of
exactly.
Yeah, the neural network.
I had one question. So what does these red and the violet regions represent? Does it represent the uh, like decisions? Like suppose there is a binary classification problem, every point which is on the red side will be classified as 0, and every point on the right side, which is marked violet, will be classified 1.
Yes, yes. So,
Okay, yeah, then what will be the outputs when the point is at the white spaces?
so that would be within the interval alpha and beta. So it will be smaller than so it will be smaller than beta and bigger than alpha.
So does the model give any prediction when the points lie in that region?
Yes, yes. So you will have a very common neural network. You will have like very common model, and this model will give you something between -1 and 1. And then this alpha and beta are two constants chosen between -1 and 1. And then when the point lies in the two level sets fx equals to alpha and fx equals to beta, you will have a prediction, of course, but we're trying to show that you can actually measure the distance between the two level sets, fx equals to alpha and fx equals to beta, and then use that to sort of measure robustness.
Okay.
Yeah. So basically, we showed that boundary thickness defined in this way strongly correlates with the neural network robustness. For example, in this experiment, we show that the robust generalization accuracy of neural networks trained using adversarial training with different hyperparameters correlate well with the boundary thickness. Each hyperparameter can be viewed as a way to change the thickness of the distance boundary. So we have said that boundary thickness is a generalized concept of margin. So why do we say that? Well, this is because we have shown that margin is a special case of thickness under some certain conditions. So boundary thickness is indeed a more generalized concept. But you may still ask, how can we show that boundary thickness goes beyond margin? Is it just always measuring something? Is it just always measuring something similar to the margin? So in the following, we show 6 different reversely trained neural networks. So in the following, we show 6 different adversely trained neural networks that have different levels of overfitting, where the overfitting is measured by the gap between robust training accuracy and the robust test accuracy. So we can see that if you measure the boundary thickness, you can see the difference between different trained models, and the thickness is indeed correlated with the extent of overfitting. But when the decision boundary becomes thicker, the robust generalization gap is reduced. So indeed, it gives a measure of how much overfitting you have. However, if you look at the margin, clearly there's no such difference because all of these curves are sort of similar to each other. So here are some more examples in which thickness can show you different levels of overfitting of the adversely trained model, while margin cannot. So indeed, boundary thickness shows something more than margin. So actually, there are some other known issues of margin that we try to avoid here. First, the exact margin of a sample is usually hard to compute, especially for high-dimensional nonlinear functions. So we can only compute the approximate margin, and it's hard to know how good the approximation is. The second one is about adversarial training. If you think about adversarial training, it's actually a max margin type of training. I guess in fact, it might be the most commonly used max margin training methods these days, because you basically apply some adversarial training samples, and that is like trying to improve the margin of the neural network. But the problem is that adversarial training harms natural accuracy, because there's usually a natural trade-off between robustness and natural accuracy. So this is the second problem. Third one is that the conventional decision boundary only concerns one level set, which is the level set that you will change the prediction. So by introducing boundary thickness, we effectively consider more than one level set. That is also why boundary thickness is a generalized concept of margin. And actually, you may ask, like, how do we choose the correct level set when we actually measure the boundary thickness? So our experiments show that as long as you don't choose something like very, very extreme, for example, you don't choose something like beta equals -1, alpha equals 1, which can actually give you something sort of similar to margin. If you do that, then you cannot really have something meaningful. Sorry, I mean, you don't have something that can actually measure the robustness. As long as you have something that is sort of between, for example, 0 and 1. Let's say that you choose alpha equals to 0.5 and beta equals to -0.5. You can have something that can measure robustness. And we have done a lot of ablation study to choose different beta and alpha, and all of these results show that we can always measure the robustness. Okay, so just to summarize our results, maybe our first result. So thickness is a generalized concept of margin, and it can measure something more than margin, which is the extent of overfitting of adversarial trained models. Then our next result is that a thick decision boundary reduces the so-called boundary tilting issue. Just to remind you, boundary tilting means that the decision boundary lies very close to the data submanifold. So in our theoretical analysis, we proved the result for a linear model. For a linear model, boundary tilting can have a more clean way of definition, which is basically the cosine similarity between your weight vector and the hard margin SVM solution. This is because the hard margin SVM solution can be viewed as the solution that is perpendicular to the data submanifold. And if the cosine similarity between your solution and the max margin solution is large, it means it has a small boundary tilting. So this is our second result. Then our third result is that the so-called mix-up training is the minimax solution of thickness optimization of a binary classification problem. So I explain what I mean by this sentence. So first, what is mix-up? Mix-up training means that instead of training on the original samples, you do a certain type of data augmentation by linearly combining two samples into one. So let's say that you have two samples, x1, y1, and x2, y2. Then a mix-up sample is the linear combination of these two samples using some constant lambda. So instead of training on the original pairs of samples, you actually train on these mix-up samples. So this is mix-up training. And then we say that mix-up training is the minimax solution of optimizing thickness, where the max is taken over all the functions, all the neural networks, if you restrict your model to a neural network. And the min is taken over all the pairs of level sets parameterized by the two parameters, beta and alpha. So why do we prove the theorems? We basically want to show that in order to achieve a thick decision boundary, one can use mix-up training. The mix-up training is a very low complexity way to achieve a thick boundary. And it can give you a little bit of reversal robustness and a little bit of improvement in the natural test accuracy. Usually these two things seem to contradict each other. If you want to achieve a reversal robustness, you will need to sacrifice natural accuracy. But it has been shown that the mix-up can actually improve the robustness just by a little bit without sacrificing natural accuracy. And we think it is because of the increase in the boundary.
I have a quick.
So does mix-up training ensure that you only find so like linear classifiers or your two, if you're a two-class problem, that the two classes have to be so convex for this to work? Because it looks like it's looking at all the convex combinations of the samples here.
So it's not necessarily convex. So it's more like a piecewise linear function. So if you think of for example, the so you can think of it like this way. So let's say that we have a bunch of red points and a bunch of blue points, and then you connect each red and blue point. You connect a line, and then on this line, you should try to make sure that the function is linear. And then you have a lot of combinations, right? You have a lot of connections, right? And you want to make sure that on all of these connections, the function is linear. So that is what mix-up gives you, but that does not necessarily mean that the function itself is linear.
So which function is this that's supposed to be linear?
So this is what I mean. So what I mean is that when you train a mix-up model, then the function that you expect to have when you train this mix-up model will be a piecewise linear function.
So is this the function that is defining, so like a regression function or a function where the positive values are positively labeled and the negative ones are negatively labeled? So you're saying that has to be linear in between data points?
So this is the function after the softmax. So let's say that you have a neural network and you have the input x, and then you take out this vector after the softmax value. So that function has to be piecewise.
And what class of networks does your theorem apply to? Does it apply to certain kinds of networks?
It actually applies to all functions. So it does not not have any restriction.
I see.
Can the functions be underparameterized functions also, or overparameterized?
Yeah, that's a very good question. So I guess yeah, maybe I haven't really stated this theorem like clearly enough. So I guess the thing is that what we want is this function to be able to completely completely fit these samples and also on the lines between them. So it's like the function has to have enough capacity to fit all of these samples and the connections between these samples. So of course it requires some complexity requirement of the function itself. But I guess this theorem sort of shows that mix-up training is a way to increase thickness, but it will also show using experiments that indeed a mix-up can increase the boundary thickness. Thanks for the question. So here I'm showing you the 3D visualization of mix-up versus natural training or standard empirical risk minimization. So the different colors in this plot show the different level sets. The level sets of mix-up are more separate from each other, but in natural training, they're mostly tied together. So you can see that mix-up does increase the boundary thickness. Then I'm going to show you some measurement of the thickness of different neural networks. So the purple ones are trained.
Sorry to interrupt. Could I see the previous slides again? I'm still trying to understand that visualization of the boundaries.
Yeah.
So if I'm looking at the picture on the right, I actually see two slices of the decision boundary. Is that true? Or yeah. What I'm, how do I compare left and right, essentially?
Yeah, so basically the way that I'm plotting this figure is that I first choose one sample, and then I choose like 3 different directions, and I try to predict, as I try to like plot the prediction values of this function on these 3 directions. And then you see a decision boundary on the right because this direction actually crosses with the decision boundary. So you can see that the function changes from one to the other. And on the left, it's like decision boundary is very thick, and then you cannot really let the decision boundary change very easily. So basically, the way to look at these 2 plots is that if you look at the one on the left, the level sets are very separable, right? So they are sort of have a distance between each other. And on the right, if you look at the level sets, they're sort of tied together. So in that case, it's like if you, yeah, so that does that, so
in a way that, can I think about it as, in the right-hand side, the decision boundary are defined by what you call level set, right? You have a continuous function. Each of the level set is sort of a boundary. In the left-hand side, you have sort of a step function where the decision boundary is sort of by itself, by definition, is interval set by definition. So it's a range of values. So you're saying that in the right, you said function value equal to 0 is my decision boundary. On the left-hand side, you say the function value between minus epsilon plus epsilon is my decision boundary. No?
Yeah, so I guess I have to clarify here. So basically the way to define decision boundary is the same. So the thing is that if you think about, I mean, if you look at the way that people define decision boundary, for example, here you have this function fx that can give you value from 0 to 1, right? So in this case, it's like the decision boundary is always the level set that you have fx equals to 0.5. So that's the decision boundary. And then the decision boundary thickness is like you look at 2 level sets. For example, fx equals to 0.25 and fx equals 0.75. And you sort of measure the distance between these 2 level sets. Right? And then on the right, you can see that these 2 level sets are very close, right? Because they're basically the same thing, right? So if you look at this decision boundary, they are basically they basically collocate, right? So if you actually measure the decision boundary thickness, you can have something that is very small. But if you look at the left one, and you use the same definition to measure boundary thickness, you can see that the level set, which gives you fx equals to 0.75, and the one that gives you 0.25 are sort of separable, right? So that is why I say that the decision boundary thickness in the left one is large.
Okay, thank you. Actually, do you mind showing I know you showed 1 slide of the definition of the thickness, and I think we we didn't spend much time on it. That's probably is the root of my confusion, is actually a precise definition. Yeah. Okay.
So basically, this definition is just like writing out the mathematics of like the distance between the 2 level sets. So there's nothing fancy of this definition. Yeah.
Okay. All right. Thanks.
Okay. Okay. So so then I'm going to show you some measurement on the thickness of different neural networks. So the purple ones are trained using Mixup. The right ones are neural networks that are trained in a normal way. And the blue ones are those trained without weight decay or L2 regularization. So that is sort of artificially generating some overfitting in the training by not using any regularization. And you can see that for all of these different models, mix-up training achieves the largest thickness, while when the network is overfitting, the thickness goes down. Then to show you that Mixup indeed improves the robustness, we look at the out-of-distribution accuracy. Just to remind you, out-of-distribution robustness means the robustness when you have these common corruptions and perturbations on your data. And if a model is more robust, it should be able to tolerate these out-of-distribution transforms. Okay, so these are the results. In each plot, again, purple means mix-up. Red means normal training, and blue means training without using any weight decay or L2 regularization, in which case you will have severe overfitting. Then you can compare the results on the last slide with the boundary thickness. And if you put these two plots together, you can see that indeed the training methods that achieve a higher thickness, which is mix-up, also achieves higher out-of-distribution robustness. So to quickly summarize, boundary thickness is a new metric that first explains robustness because it can measure overfitting in a versal training and it can outperform margin. And second, it is easy to optimize because you can basically use mix-up. Close to the end, I will talk about some new technique that is inspired by boundary thickness. So until now, we're basically looking at the distant boundary between different classes of data. However, if you look at the whole data space, usually the place that you have data is extremely small. And we tried a lot to optimize the boundary between these two different classes, but like this is just a very small space in this entire input space. So you might ask, what about the boundary between data and noise? What will happen if we try to make the decision boundary between data and noise thicker? We have mentioned that mix-up scheme is a way to increase boundary thickness. That's we want to use mix-up again to increase the boundary thickness between data and noise. So here I'm trying to show you how to do this. We'll first introduce an additional class in the data set, which is just a pure noise. If you use CFR 10, you will now have the 11th class, which is pure noise. So now the neural network also needs to learn to classify noise from the true data. Then we mix up both noise samples and clean samples. We show that by mixing clean samples with pure noise, we can further increase the robustness of mix-up. As you can see here, noisy mix-up improves the robustness of ordinary mix-ups significantly. Also, we have measured the decision boundary thickness of noisy mix-up versus mix-up. We see that noise-augmentation can indeed increase this thickness. So this is another way to show that boundary thickness is important because when you not only increase the thickness between clean samples, but also between clean samples and noise, you can still improve robustness.
I have a question. Doesn't the model now become different because you have more classes and you have extra clean versus noise thing? So how can you compare? Like how you are saying that it's the same setting we are improving the thickness and versus.
So Yeah, so the number of classes indeed increases by 1, but when we actually calculate all of these accuracy, all the black box accuracy, we sort of try to make sure that we are making a fair comparison. So if let's say that you have a sample that is classified, so let's say that it is originally a noise sample, and it is classified to be, let's say, I don't know, maybe let's say a chair or something, then we will say that this is actually an error. So so basically we're trying to make sure that oh, actually sorry, I guess this is like a little bit different. So we actually use the same test data. So in this case, it's like we only have 10 classes of samples in the test data, right? And then if let's say that you get a sample that is from one of these 10 classes, and you classify it to the 11th class, then we'll say it is actually a different, it is an error. So basically, we're trying to make sure that we're making a fair comparison.
Somewhat like the noise, if there is any noise which are mixed up in the adversarial set, then the model should easily classify it as a noise. That's the main kind of, I think, idea behind this, like, because the perturbations are mostly noise, so that's why we want them to classify quickly as a noise, something like that.
Yeah. I think that's a good point. But I guess, yeah. So what we want to say here is that boundary thickness is really important. But as you say, it's like if you can let the neural network learn to classify noise, that is also like a very good thing, right? So actually, I think we actually did some experiment to try to differentiate these things. It's like we try to like just let the neural network to learn to classify noise, but that cannot give you this large improvement. So, but it can indeed like increase the accuracy a little bit.
Interesting. Thanks.
No problem. Okay. Yeah. So let's go back to our summary slide. So now we have put another bullet point here, which is that we have used the boundary thickness to motivate new algorithms during training. Yeah, so I guess this is basically the summary slide. I can either stop here or stop on this this picture of boundary thickness in case you have more questions. And thanks for listening to my talk.
Thanks a lot. I think we logged well.
Nice.
So any questions?
Yeah, could I ask a question here? I'm trying to understand this this constraint over the mixed up, right? So when you do the mixed up, you are doing a piecewise linear interpolation of the data point X and its label as well, right? So one version I could imagine to replace it, I mean, this is a good picture you end up with, right? Is in a sense that on the left picture, I could imagine there's a local neighborhood surrounding my circle and my square. And in this case, I would imagine my local neighborhood, let's say my local neighborhood is defined by a small radius. And so my decision boundary is sort of separating, essentially, imagine each of those data point, the square point and then the circle point has a ball growing around it. And the left one is the one where the radius is very tiny, and then you're trying to find the separating boundary of this. And on the right-hand side, what I'm going to do is I'm going to say, well, not only my circle point on the right-hand side is one with a positive label, but a pretty large local neighborhood is also going to have, you know, kind of a positive label, right? So in a sense that I'm going to grow a ball of a large radius surrounding those training points, such that their neighborhood with a large neighborhood are going to have positive or negative label. And now because of that, I'm basically enforcing, in some sense, my training data in a way that I'm enlarging my sort of my size of my training data by growing from one point to like a ball of certain radius. And now under that condition, I will enforce a boundary, a decision boundary to sort of push them further away, right? So in a sense that I feel like philosophically, this is what's happening, with the exception that your underlying mixing up is using a piecewise linear thing. But I could easily, I mean, maybe correct me if I'm wrong, I could easily replace the mix-up version by just having like some form of ball kernel surrounding each training point and sort of achieving the same effect. Is that the case?
So the thing is that if you look at our reversal training, that is sort of similar to what you're talking about. So it's like if you add some reversal examples in this ball,
Yeah,
it is similar to what you're talking about. I guess the main so like one of the main difference between like using Mixup and the reversal training is that in using Mixup, you can sort of reduce this overfitting issue that people like continue to notice in reversal training, and and by using this piecewise linear function, you are sort of like imposing a stronger regularization, not just at the point of the data sample, but also between samples. So
yeah. Sorry, go ahead.
Yeah, so that is like a stronger form of regularization that if you think about it, that is sort of similar to what the reversal training does, but it's still different from the
So if I were again thinking about from the language of the kernel, right? Initially I said there's a disk surrounding it, so that is a ball kernel, and it looks like your mix-up version is really like a triangle kernel, right? Because you're damping the signal when you're moving away from the true training point. So you have this piece linear. So in a sense that I could imagine this mix-up, maybe, I mean, correct me if I'm wrong, maybe a scenario where I'm taking a linear combination of triangle kernel, right?
Yeah, I think yeah, sorry. Yeah, I think that is indeed what is happening. Yeah, but I'm not quite sure about that because I'm not very familiar with the triangle kernels.
I think there's also a question in the chat. There's a question in the chat about what are the connections between boundary thickness and model complexity?
Yeah, I see. Yeah, so that is a very good question. So sorry about that. Yeah, so I guess there's definitely a connection between boundary thickness and the model complexity. So there's actually a paper, I think, which is also published in last year's New Rips. Sorry about that. Which basically says that so there is actually a tendency of neural networks to generate simple functions. So what I'm trying to show here is that if you make the decision boundary thicker, you can sort of make it to sort of deviate from this tendency to create a simple function. And I guess that is the connection here. But I guess if we want to really make a concrete connection, we have to first define what we mean by model complexity, and if we actually have a way to measure that. Clearly, we cannot just say, okay, this model has more parameters than it's more complex. It's not as simple as that. We clearly have to have a way to actually define how to measure the model complexity.
From this perspective, one way to easily quantify complexity would be amount of time taken to perform inference on the test set.
So, but the thing is that if let's say that so let's say that you have two data sets, and one data set is very complex, meaning that if let's say so let's say that you have two so let's say that you have two data sets. One data set is very simple, in which case you just have two balls, one ball of red dots and one ball of green dots. And then in the other data set, you sort of have a similar data set, but you change some of the labels of these two balls. So it's like one data set is very clean and the other data set is very noisy. And in this case, let's say that you train a neural network on the left one with very high complexity. So you use a very large neural network. And on the other side, you train a neural network with very small complexity. Then in this case, the right one clearly has much larger complexity because the data set itself is larger. The complexity of the data set itself is larger. But the thing is that if you look at the inference time, then of course the smaller neural network will have a smaller inference time, right? So I think the inference time itself alone probably cannot give you the measure of complexity.
Yeah. I think Jeff has his hand up for a while.
Yeah, so first I want to, so thank you for coming here to give the talk, especially with your sore throat. So I want to ask another question about, I'm having a little bit trouble understanding, so the notion of boundary thickness and so like how to quantify it. So if I took my function f and I multiplied it by 10, then it seems like my boundary thickness is going to go up by a factor 10, right? But I haven't changed anything about the classifier. Or if I inserted, like, if it's has to be between 0 and 1, I insert like a sigmoid in there, it's going to have a similar effect, right, within, you know, so some range. So like I guess even after this, I still don't quite understand what it is that you're optimizing and how you are avoiding these kind of so trivial ways of increasing the boundary thickness.
Yeah, that's a very good question. I think this is not just the problem of boundary thickness. It's sort of the problem of many other different metrics that people often use to measure training. For example, people talk about like flatness, like sharpness of local minima, and like the Hessian, this type of things. And if you know, like for example, get a function and you just change this function by maybe adding some constant here and subtracting some constant there and then dividing some constant in other places, you can easily change all of these different metrics. It's like if you do this kind of things, all of these different metrics won't really be useful anymore. But things that when you actually look at this problem, you have to look at when you're actually doing the training. So if you, for example, multiply a factor of 10 on the softmax layer or something similar, doing something similar to that, and you do the training, you actually mess up the training process. So it's like what we are trying to show is that the boundary thickness is something that people can use to practically show to improve thickness. And when you want to increase this boundary thickness, you have to increase this during training. So if you, let's say that you just change it afterwards, you change the neural network afterwards, that's sort of similar to all of these different metrics, and you won't really have, you know, the thing that you want.
So, but if there are like these, so if there are these mechanisms I can do that does not change how the classification works, that so changes boundary thickness. So doesn't that imply that it's not like, so like causally the right measure, because there exist optimization techniques that keeps everything else so constant, but changes the boundary thickness, right? So
you can think this way. So let's say that you have a neural network, and then let's say that you increase for example, the last layer by a factor of 10, let's say. And in that case, of course, the decision boundary becomes much sharper, right? The thing is that if let's say you have this type of neural network and you continue to train it, then instead of having a decision boundary like the right, you will like go more and more towards the decision boundary on the left. So it's like, of course, if you only change the function, you don't do anything more, of course, that will give you the same function, that will give you the same thing. But the thing is that as long as you start training, you won't have the same function anymore. And these and this metric is sort of like useful when you're actually doing the training and sort of help you find the correct way to classify things.
Yeah, but if I explicitly optimize for boundary thickness, I could so do one of these trivial things and achieve a higher value for boundary thickness, right? So if it's not what I should be explicitly trying to optimize, then how do I? So then I have two algorithms. One is higher boundary thickness than the other. I guess I'm trying to understand why I should trust that if I know it could just be I multiplied the function by 2.
So I mean, if I understand your question, so you're asking like, is it possible, for example, I can like use this boundary thickness actually as the loss function during train? So is that something that you think is useful?
Sure. I mean, it could be within, I mean, there are two ways you could use it. One is within the gradient descent, perhaps somehow. I don't know quite how to do that. Or I'm comparing different algorithms and they're completely different. One's a random forest, one's a neural net. And at the end of the day, I'm going to use the one that has the higher boundary thickness. But it could have been the result was one function was multiplied 2 by the other one, right? So it's not, they could be really the same decision boundary. So like I'm still trying to understand why, like, what is this saying that is, so what is this kind of notion capturing? Like, is there, I think I must need to put some restriction on the class of functions for it to be meaningful, right?
So I guess the first thing is that, I mean, if you sort of talk about the way of doing optimization, we have shown that Mixup is like the theoretical optimal way to increase boundary thickness. And that when you apply Mixup during your training, you actually increase boundary thickness and sort of make the result better. And the other thing is that when you talk about, for example, these results and we'll say, for example, you have another neural network and you multiply by 2, and then the boundary thickness becomes smaller, right? So I kind of feel that this is not the right way to look at this problem. And I kind of feel this sort of like a Simpson's paradox is like, in general, you maybe have a trait of classification accuracy or robustness versus boundary thickness. But on the other hand, if you just look at, for example, some special cases, you may definitely find some special cases that actually gives you like the opposite direction, right? But I guess the things that do you want to sort of, like look at this type of special cases and find some common examples to that, or you want to sort of find something that really works in practice. So yeah, that I get, yeah. So I'm not quite sure if.
Yeah, so thank you. Yeah, I guess it's a tough question, but thanks for trying to answer it. Yeah.
There is one more question by Anna, I think. Is there a clear relationship between the dimension of the data input and the boundary thickness?
Yeah, this is, I think this is a good question. Yeah, I'm not quite sure about this. I think when you have like a larger dimension or smaller dimension, you can clearly have larger or smaller boundary thickness. I'm not quite sure there's a clear relationship.
So it's not clear to you as you increase the dimension, you want to make the thing bigger or the reverse or something like that.
Yeah, that's a very interesting question. So maybe let's say that you have some data that is sort of in the very high dimension, then of course you may likely to have a thicker decision boundary because data becomes more separable. But if you only put the data in a low dimensional space, then probably you need I mean, if you want to really fit the data, you will probably need to use a thinner boundary. So I think, yeah, I guess they are definitely related, but I'm not sure if there is any like clear relationship. At this point, I am not quite sure.
Is there time to ask one more question, Vivek?
Yeah, you can go. If
Okay. So,
yeah, okay, one. Go ahead.
okay, so is there a relationship between the strength of the attack and the alphas and betas that we choose?
Um, so yeah, so I guess I don't think there is a clear relationship between because we actually tried to change alpha and beta as well as the strength of these attacks. And what we see was that when you sort of, I don't think there's, for example, I mean, of course, you cannot really make the attack to be extremely large or extremely small. In those cases, of course, there won't be a very clean relationship because either way, you will have like trivial robustness. And as long as you choose these robustness values to be like sort of not to be the extreme values, I think it's okay.
Okay.
Okay. Thanks, Yang, for the talk. Aditya has to leave because of another meeting, but thanks for the talk and giving the talk despite bad throat, and and I hope everybody enjoyed. I like the presentation and the because theory talks are generally difficult to explain, but you did pretty good job in explaining to people. Thanks for this.
This is a really good discussion. Thank you.
Everybody, thanks for attending. Bye.